Hi, my name is Berglind and I'm going to explain the superposition theorem from experiment 2 and show you how it can be applied in circuit analysis. Solving circuits with more than one independent source, one method people may think of is superposition. Superposition is one way to determine the contribution of each independent source to the variable and then add them up. Superposition can only be applied to linear circuits, that is, circuits whose output is directly proportional to its input, but this graph describes a linear function. This is the circuit we will work with throughout the video. It contains two independent voltage sources, E1, which is 3.3 volts, and E2, which is 5 volts. As we are going to measure voltage at node A and the current through R4, the superposition theorem can be used. It is extremely important to decide in which direction we are going to measure or calculate the current each time. Therefore, I have chosen to always measure in counterclockwise direction. To apply the superposition principle, we only consider one independent source at a time, while others are turned off. Our circuit contains two voltage sources, and when turning a voltage source off, we replace it with a short circuit. But can superposition theorem be used to find the total power in the circuit? We are going to answer this question after performing the experiment. So, let's begin. First, let's look at the equipment used. We need 5 resistors, 2 voltage regulators, 9-volt battery, and a multimeter. Now it's time to build the circuit. The 3.3 voltage regulator is connected to the breadboard. The 4.7 kilo ohm resistor is connected in the same row as the middle pin of the regulator, but that is the output pin. As the 22 and 10 kilo ohm resistors are mutually connected to node A, along with the 4.7 kilo ohm resistor, we must connect all of them in the same row. The same applies to node B, where the 22, 33 and 6.8 kilo ohm resistors must be connected to the same row. We can see that the 10 and 22 kilo ohm resistor have been connected to the ground, or the blue rail. Then we can connect the 5-volt voltage regulator. The third pin is the output pin, and therefore we connect that pin in the same row as the 6.8 kilo ohm resistor. The middle pin is a common pin, and it's connected to the blue rail, the ground, with a jumper wire. To deliver power in the circuit, we must connect another jumper wire from the red rail to the input pin, which is the first pin. Nearly the same is done with the 3.3 voltage regulator. The only difference is where the jumper wires are connected, because the function of the pins is not the same as in the other regulator. The first pin is the ground and the third pin is the input. And now the circuit is finally ready. Let's disconnect the E2 or the 5-volt voltage regulator and replace it with a short circuit and measure the voltage at node A and the current through the 22 kilo resistor. We begin with disconnecting E2 completely from the circuit and replace it with a jumper wire. To measure the current through the resistor, we remove one end of the resistor from its row and replace it with a jumper wire. Because I decided to measure the current counterclockwise, I put the red probe on the end of the resistor I removed and the black probe on the jumper wire. The measured current is minus 72 microamperes. Remember to put the resistor back in place before measuring the voltage at node A. When measuring the voltage, I'm measuring from the node to the ground and get 1.98 volts. Let's insert these measurements in a table. After putting E2 back in place, we short circuit E1 the same way as before and perform the same measurements. Don't forget in what direction you are measuring. Again, we insert the measurements in our table. 136 microamperes and 0.42 volts. Finally, the last part is to repeat these measurements with both E1 and E2 in the circuit. We get 63 microamperes and 2.42 volts. When adding together the values we get from E1 alone and E2 alone, we almost get the same result we get from E1 and E2 with a small deviation. This states that superposition can't be used to find total current or total voltage. But can superposition be used to find the total power in the circuit? The short answer is no. That is because power is a nonlinear function. The relationship between power and voltage or current is nonlinear. We can easily see that because the voltage and current are squared in the equation. When drawing graphs of linear and nonlinear functions, we see that the main difference is that nonlinear function does not produce straight line when graphed. Finally, let's open LT-SPICE, but that is a circuit simulation program. We start by building the circuit. First, we choose the appropriate components. And then we apply the value for each. Next, we connect the components by using the wire tool. And don't forget to add the ground to the circuit, otherwise you won't be able to simulate. And now we run the simulation by choosing the DC operating point option. But to understand the results more easily, let's add label for node A. Now we short circuit the 5 volts and simulate. And the same step is repeated for the 3.3 volts. Here we can see the summary for the results we were looking for. We can notice the similarity right away, and because of small deviation between the experimental and simulation values, the results of our experiment can be considered significant. To make the calculations easier, we are going to use LT-SPICE to prove that superposition cannot be used to find the total power dissipated. It can be done when performing the simulations. When hovering the mouse over resistor 4, the power dissipated by the resistor will appear down in the left corner. When adding the power measured when the circuit contains only E1 and then E2, we clearly do not get the same result as when the circuit contains both E1 and E2. However, we could use superposition to find the total current or voltage and use those values to find the total power. Thank you for watching the video.